Again, I'm using it because he has some great animations. He also has a video on this too. So it's great just kind of watch it through just to see it. There's a lot going on here, but basically the idea here, you can see this green block right here is an LSTM. And essentially what's happening, he's kind of animating this right now, is that basically a vector gets fed in here, goes to the LSTM, same thing as before, there's outputs, basically other states, and then an output to the predicted, like the Y value. So we'll see what that looks like. So he kind of talks about the vanishing gradient problem. We're not going to really talk about that too much. So LSTMs and GRUs. So I honestly think like this stuff is like if you look at this, it's pretty complicated. And honestly, whenever anyone sees like an LSTM for the first time, they're like, whoa, like, what is going on here? And just know that basically it's just showing a sequence of steps. So I'll kind of walk this through here. But the way you can kind of think about this, and the way I kind of think about it, is that this LSTM can really be broken into and he kind of shows it here, but I'm going to kind of write it out. It's like if you were to like make this a little easier to read, is that you essentially have like your long-term memory. So I'll just put like LT. Okay, so long-term memory. You also have your short-term memory. I'll put ST here. Okay, you then have an actual like input. Okay, so sometimes people call this an event, but we just call it input, right? Okay, so this would be like your word or like your phoneme or whatnot, and then we'd actually output a new long-term memory. And we also output a new short-term memory. Okay, so this long-term and short-term memory basically would be produced through here. And the way you can think about it, there's a few gates. There's a forget gate. You can see here a forget gate, our learn gate. This is kind of like where things are actually learned. And then also our remember gate and our forget gate. Or I'm sorry, not forget gate, our use gate. Forget it's over here. So if you label this would be forget, learn, what did I say over here? Remember and use. And basically you can just say, oh, this gets fed into here. So for example, this part gets in there, and then basically these parts will get fed in a certain way. Yeah, just like this. So basically we have our each part of either the learning gate or the forget gate. Okay, these gates basically will determine what things we should remember and what things should we just not remember anymore. And this basically allows us to kind of keep in mind those kind of parts. So you can kind of see, if I kind of walk this through a little bit, is that, let's see if I can do this right. Oops, I have to have a mouse. So, nope, oh, sorry. Okay, so I'm gonna kind of walk this through a little bit. Is that what would we have? We'd have our short-term, our long-term memory. And basically we'd have our short-term go in through here, okay? And I'm just looking at my notes here for in this learn gate. So you can imagine like this learn gate, or he calls it the input gate, but basically this information gets pushed through here. So this is our input, this is our short-term, these come together. And basically you can come across into this input gate or this learn gate and says, okay, well, this information is a sigmoid, basically chooses out what's important between the short-term memory and its input. And basically that would get passed into here, okay? And then we would just follow this through this cell right here, all the way through. If you followed in for the forget gate, you'd have the long-term memory just go through here. And basically for the long-term memory, it says with this little, pointwise multiplication. Basically, this is just saying, all right, let's go ahead and get rid of some of the information that is my long-term memory. And then that will get passed over to this cell. So this cell right here will eventually be the actual output right here. And so what will happen here is that this output here will keep this, the new information, the short-term memory and the long-term memory with basically some of it forgotten, and put it out into a new part of the cell. And this will come out as a new long-term. And we can see something similar is that we have our short-term memory going through here, our event going through here, and combined such a way, and it will consider this kind of long-term, short-term part going through here and going through part. And let's know that basically these are different activation functions, tanh and sigmoid. And so I don't know about you, but like the first question I had is like, how does this work? Like who decided this works kind of deal? And it turns out basically comes down to the fact that it just does. This architecture works in this way. People can tweak it. So like know that, if you are feeling adventurous, especially, you can tweak these kind of architectures and see if they do perform better and such. A lot of machine learning at this level, at least as of right now, is a lot of just saying, does it work? And, a lot of times it's not really sure. Why do we use a TANH over, you know, a ReLU sometimes? Sometimes it just works better. And that's just kind of like the approach going through. And that's a lot of like testing and, you know, analysis. Just know that that's kind of generally what happens right now. With a GRU gate, it's a lot simpler. We don't, instead of having a long-term and short-term memory, we'll actually have just one working memory. So you'll just have one memory and you'll have one input. So if you imagine here is that if I were to write down, this is our like, you know, our memory, and this is our like our event or input, right? And basically this gets fed in through here. One is a reset gate. Basically you can think of it like thinking of like, well, he calls it a reset. That's not what I would call it. Is that right? Sorry, I want to make sure. Okay, he calls it a reset gate. I personally call it like an update gate. This is more like taking the information and the input and then the memory and finding a new part. And then our update gate actually will take our working memory and stuff to actually give us an output. But the idea here is that essentially you will have this memory come out and there's just one versus short-term and long-term. And it turns out GRUs actually work pretty well. Again, it's just like, why does it work really well compared to an LSTM? Well, just turns out it just works better. Okay, cool. So yes, so let me go ahead. I think that's all I really wanted to show on this part. This is kind of like showing like, if you were to watch this part, so you can imagine this is our RNN. So like in our RNN, we have our different spots, but instead right here, we have our different, well, I guess no, this is an RNN in this case, actually shows. But you can see like, we all stack them together, we put in each input, and basically they get fed into the next part and eventually to an output at the end, or if there's right here, there'd be an output at the very end of this part, okay? So you can kind of see, you guys showing like, okay, how this would come in together, how these parts combine off to the side from an RNN. So you can imagine from our RNN before is that we had our input and then a previous state, put those together, and it outputs one new thing, right? So it kind of goes through different, different examples, like, how we would actually pass information through, how it changes and such like that. But hopefully you kind of get the idea of like just passing information. That's where it comes. Then he kind of shows what the LSTM looks like and how that works. And I think he has an animation if I have this right. Okay. Yeah, so this one right here, he has a few sequence of animations. So you can see, like, for example, if you had the input and the previous cell state, which is kind of like, I think I said that short-term memory, right? So this is our short-term memory here being passed in from our long-term memory. So remember, previous cell state, that makes sense calling it the short-term memory. Basically, those get passed in together to get some new information. And then you can see the same information actually gets passed into a different way. In this case, it actually gets passed into these two parts, combined over into one part. And again, why do we have to pass into these parts? In reality, it just comes down to it works better this way. And so you can see here now that we have basically one new point right here of the long-term and short-term memory. And these are structured differently from the short-term memory and the input. And note this is different from the short-term memory and the input from this point, okay? So the next step will actually be on our cell state, which basically the cell state is like what's actually being traveled through. And you can see here, this short-term and our short-term and our input gets put through here and gets combined. I call this the long-term. He calls it the cell state, but you can think of it like the long-term memory, what it has over time, what's important. And basically combines this, okay, from the stuff that you already know, plus what already you just learned from the input and short-term memory, combine those together essentially. And then we have a new combination here. And essentially that will be our new long-term memory or our new cell state, okay? And you can see just kind of traveling through. And eventually this will travel outward, but we'll also use our new cell state to predict on top of the, the new state, the input state. So you can see here is that we have our input going through here, and we'll actually pass it through another sigmoid, and we'll actually combine these two parts, and then we eventually become our new short-term memory. So this will be the new information that will get passed on to the next LSTM cell. Okay, so again, I would say like this right here is like the path from the long term, which kind of makes sense hopefully, is that basically you have this forgetting part, then you have kind of like this new information being combined with the input and output, okay? And then we basically have this new short-term memory here, okay? So that's kind of the whole thing. And he has a little pseudocode here, but basically you can see it's a little more complicated to have to go through parts, but essentially it would be the same thing, is that you're just defining these parts, okay? In the GRU, so just kind of going through this one a little bit, I don't think he has an animation on this. Yeah, again, this is the same information, but instead of putting in long-term and short-term memory, or he calls it like the cell state, essentially there's one cell right here, or one like memory unit right here with the input. So this would kind of continue to go through. And again, note that the reason why this is different than just a regular RNN is that this is not a neural network by itself. It's a very specific structure and architecture that actually will produce this kind of thing. And again, why does this architecture exist? There's some intuition of it, like mathematically, but in the end, it just comes out like, oh, this turns out to work really well. Okay. So that kind of ends it for recurrent or LSTMs and GRUs, basically these cells that keep memory. Any questions overall? Okay, sound good? Cool. Yeah. You can go like really deep onto these parts, but just know that basically every time you solve with an RNN, you could replace those like individual cells with an LSTM or a GRU, and that would essentially make you a new network. Okay. I did want to show this paper really quickly. This is actually a really cool one. Basically shows like how a GRU works. Also talks later about an LSTM. Basically, it's kind of, it shows you another like gates and stuff, but the idea is the same. And then of course you can tell we always have like, you know, this mathematics actually trying to find the gradient and stuff like this. So, you know, you can come through this, but I just wanted to show like another way that of them presenting it. So you can hear, for example, they have an LSTM and they can input this part here. But anyway, I thought it was kind of an interesting way that they presented this. Okay. So the last thing I'm going to talk about, just very, very briefly, is just the concept that there are something called a bidirectional RNN. So again, this is from the curriculum. And then the idea here is that we have a bidirectional RNN. So you can imagine each of these like, you know, squares essentially is information getting passed forward, but also just like, or sorry, in our normal RNN, we would just have all the information passed over. It's like, okay, the next step, the next state, and going through here. Bidirectional basically allows you to, in the feed forward, so I want to make this really clear, it's not back propagation. It's that when you put in, for example, this vector x1, you input it also to A1 and A1 here, okay? And those parts would get passed into our output. And then what would happen when we go to put our x2, this state comes out over here, okay? And we go this part. But what's interesting is that this will actually go back and be part of this x1 part. So what happens is basically, remember you're training this whole thing at once, right? But the idea here is that you essentially will use some of the past information in the future information essentially to go through it. So the way you can kind of think about this is like you see a sentence, it might matter if you talk about, you know, what the, what's it called? Oh, I think you give an example right here, like teddy bear, right? So teddy bear versus Teddy Roosevelt is that you need to know what Teddy actually means, right? It's like Teddy could be a teddy bear or it could be Teddy Roosevelt. Well, if you only look at the past information, there's no way for you to tell like what does Teddy actually represent. So this is where a bidirectional basically allows you to keep that information going the other way. And know that it is a one feed forward pass and that we train it across the whole thing. So just to kind of know is that it's hopefully it's not back propagation. That's the important part. Okay. And just know this is another method for you to basically have, especially for natural language processing, where words in the, you know, said later on or like written in text can affect the previous words, and the previous words can affect the current words. So you kind of have this like go back and forth. And again, it all comes down to us when we're training these kind of things is that they're trying to find, what's it called? The minimum cost, right? And so eventually it'll hopefully come across things that where these values, these weights would be the same, or not the same, but a good number. Obviously, you can probably imagine what might be some disadvantages to this. It's just the fact that it's just more complicated. It's going to take more time for you to train these kind of things. So bidirectional can be used, but aren't always like the go-to part. If you can do well with a typical RNN that's not bidirectional, then you probably should just go ahead and use that, just because this will take the training a lot longer. As you can probably imagine, there's now essentially twice as many inputs going through here, just from having the fact that it can go backwards. Okay, cool. Yep, so that's kind of all of it right there. And you can see here from Keras, again, using a cat package like this instead of you making it from scratch is great. But that's why I always like to go over like how this actually works, because this is the whole thing right here. But you can obviously see it's like, okay, well, we have an LSTM right here. We have our different input shapes. But like, it's nice to know how these things work, so you know when things go wrong or how you can improve on them, or or if someone says, oh, there's this new tool, you actually know, say, hey, like I actually know what this is like. This is like an LSTM, but a little change in structure. So yeah, all right. Well, cool. Any last questions then, since that kind of finishes up all I had? Awesome. So I guess that is it. And I'll go ahead and stop my recording.